Evening, everybody. Welcome to Rod's Office Hours, where we're going through some industry insights. This week's topic will be focused on electric submersible pumps, form of artificial lift. Pretty exciting topic, and should be hopefully you find it very enjoyable. I've enjoyed them for a number of years. So in artificial lift, we've covered a few things. We've talked about rod pumps and pump jacks. We have gas lift valves. That's still to do. And progressive cavity pumps, or a bit of a Archimedes screw type of pump. And then tonight we're going to talk about electric submersible pumps. And then there's also plunger lift, which is sort of a form of gas lift that's with a plunger in the tubing. All these forms of artificial lift have different applications. On land, probably rod pumps and pump jacks are probably most popular. And then offshore is probably gas lift and electric submersible pumps. The ESPs, so electric submersible pump, ESP, also quite common onshore, so is in use offshore and onshore, and also used in water wells, like drinking water wells, also geothermal wells. So a pretty versatile pump, and so we'll get to talk about that tonight. A bit about myself. My name is Rod Gibbons. I've been a petroleum engineer and entrepreneur in the oil industry for 30 years now. In business with my wife, Willow, and I've worked in, this picture's from Australia, but worked in a number of countries and continents, onshore and offshore, and both are very enjoyable. Both have interesting aspects. So I'd like to talk in this office hours over some of the practical implications of engineering in the oil industry. Just as a refresher, I'll put this formula up here again because, as I said earlier, this is kind of the formula for production engineer, for petroleum engineers, which is pressure equals density times gravity times height. And the idea being, the deeper you are in a column of fluid, the more pressure is required to get gas or lighter liquids back to surface. So that's kind of our whole principle of oil and gas production wells. We also covered before the idea of inflow performance and vertical lift in tubing. So a natural flowing well and a dead well, and of course, when a well dies, the inflow performance from the reservoir doesn't have an intersection with the tubing size for a natural flow. And one of the solutions there is to then put artificial lift in the well. And the form of lift that we're going to talk about tonight is electric submersible pumps. And so what is an electric submersible pump? Well, it's electric. You can submerge it in water and it's a pump. Okay, what type of pump? It's a centrifugal pump or centrifugal pump. I've never been able to kind of keep those things straight, but basically the principle is that you have water or liquid coming into the center of the pump, and you spin the impeller, the inside of the pump, and water then gets pushed out towards the edge of the pump, and then it gets pumped into the outflow piping. So in a rod pump, we were using a ball and check to physically displace the fluid. Here we're going to spin it around, and so I guess so these guys here on an old-fashioned merry-go-round, they've had the brilliant idea to put a scooter tire against the merry-go-round, if they were liquid particles and this was a pump impeller, then what inevitably happens is that the force spins them towards the outside of the impeller. So I don't recommend doing this. Well, not at all. This doesn't make any sense. But it highlights the point. A centrifugal pump uses centrifugal force, and so because as they're going in this circle, they want to keep moving straight. They actually, you appear to feel to get flung off to the edge of the merry-go-round. So that's what happens to our water or our liquid when it comes into this pump stage. This is a pretty simple example of a single stage pump. If you put a bunch of these impellers together, you'll get a multi-stage pump, and we'll have a look at that here shortly. So just on to the next one. So centrifugal pumps are common on surface and downhole as electric submersible pumps. So this is just an animation of a surface pump. The only difference being at surface you have lots of space, whereas in a well we have to keep it all into a very small diameter. So it's a little bit easier to see. So you have the casing and an impeller, and that's the spinny bit. And so you can see here the impeller is spun around, liquid comes in and gets spun to the outside using that same centrifugal force. As it gets spun to the outside, it then gets pumped out the discharge of the pump. In this example, this is an electric motor. There's some thrust bearings here and this shaft. All these components are the same in centrifugal pumps. They just can look a lot different. Also, some vacuum cleaners work on the same sort of principle, where it's just taking air in and spinning it around and then shooting it into the vacuum bag. So again, this is the simple physics of it. What does it look like in a multi-stage pump? So again, this is a surface pump. So just for illustration purposes, again, because it's bigger, it's easier to see the pump stages. So here, this green bit would be the casing, or the stator. It stays static, and the inside moves. So you have your electric motor, and then you see here we have multiple stages, all stacked together. And these pump stages, these impellers, if you think of them as merry-go-rounds, the shape of them determines how much fluid can flow through them. And every time, so this is the suction, the intake. So it's a combination of the impellers, the geometry of the impeller, which is spins on the shaft, and the geometry or the shape of the static casing. So water will go in and enter into that impeller. It'll get spun around and it'll get flung to the outside. As it hits this casing wall, it then gets directed up into the next pump stage, and it gets flung around again, and so on and moves further up. So the pump, the water pressure is actually going up every pump stage. So here it might go from 0 to 5 psi, 5 to 10, 10 to 15. It's the same motion, and they're all connected to the same shaft. So this makes this a very, in a way, simple system. And there's not much, in our rod pump example, that positive displacement was hitting the fluid every time. This is a much more rotational motion, a little bit easier on the equipment. So that's how, when you put multiple impellers and pump housings together, it's a multi-stage pump. And that's what most oil field electric submersible pumps are. So how does this look like when we put it in a well diagram? Well, things get a lot more compact, because at surface you have lots of space to put your motor and your pump. You can spread it out. You want to make it easy to maintain. When we go into a wellbore that we've drilled, now we have very limited space. So if we have, say, 7-inch casing, the entire pumping system all has to fit within that diameter. Luckily, the wells are quite deep, so we have lots of length we can play with, but not much annular space. So down here at the, and so this is typical well completion like we covered previously. You have your formation, reservoir, perforations, and you'll get oil, water, and gas coming in from the formation, entering the wellbore. Now, in the early days, the well would probably flow naturally, so we wouldn't have to worry about any form of artificial lift. But if the pressure dropped here or the water cut went up, then we'd have to install artificial lift to keep the well going. So, and of course, this cartoon is not drawn to scale. Normally, if a pump was 2,000 meters deep, then the pumping system might only be in total 50 meters. So from bottom up, so if we start down at the bottom, lots of times you'll have a monitoring tool on the bottom, like a pressure sensor, because what you want to make sure is that you don't pump the fluid all the way down and then you no longer have any fluid available. So lots of times you'll have a pressure or temperature sensor just to keep things from overheating or from running out, pumping down too low in pressure. Then, but really the big component first is the motor. So this is an electric motor, an electric submersible pump. And so as your reservoir fluid is coming in, it flows outside past the motor, and that actually helps keep the motor cool, because this motor is making a lot of heat because it's electric motor. Reservoir fluid flowing past it helps take the heat away from this motor and keeps us makes it last longer. And then from the motor, there is then a motor protector or seal assembly. You don't want to have reservoir fluids going into your motor, because then your electric motor won't work. Same as almost every electric motor, you don't want to get it wet. So this is a seal. There's a shaft going from the motor up to the pump. So these seals keep reservoir fluids out of the motor. Then you have a pump intake, and that goes into basically a gas separator. So in that centrifugal pump, it does really good with liquids. It can pump a lot of water, it can pump a lot of oil. Putting gas in there, it doesn't do so good with gas, because as you spin gas around in that centrifugal pump, it's hard to move it to the next stage because it's compressible. So you could end up gas locking your pump, where you get a bunch of gas in there, and then you spin it around, but rather than pressure up and go to the next stage, it just compresses and stays where it is, and then stops the flow in your pump. And then you have to flush the pump with liquid to get it pumping again. So a gas separator helps minimize the gas that's going through the pump stages and make sure that the oil and water go through there. Then it goes into the pump housing, and then up through inside of our standard sort of tubing that we run in a well. But of course, something that we have to think about here is this is an electric pump. The motor's down here. We also have to run a ESP power cable from surface all the way down to the pump motor. And we do that on the outside of the tubing. And that supplies power to the motor that gives energy to the reservoir fluids. So we'll cover each one of these components just a little bit more close up. So starting with the ESP motor, this is a picture of somebody actually winding the motor. So it's a standard electric motor. It's got on the outside, the stator, the part that doesn't move, is called the stator because it's static, so it doesn't move, stator. This is basically a bunch of copper wire thread through, back and forth, wound through this outside housing. And then the rotor, which is the inside part, is an iron core with magnets in there. And what happens is when you apply an electric current to the rotor, that causes to the stator, that causes the inside rotor to rotate. So, which is the same thing that happens when you turn on an electric fan. It's that same thing happens. There's a coil of wire on the outside, and that turns applying current to that wire makes the metal shaft and the inside rotate and turns the fan. We're going to do the same thing with our pump. We just apply probably more current than the fan in our house, but it turns the shaft. You see, could you kindly come back on what gas locking is? Oh, sorry, did I miss that question? Oh yeah. Okay, thanks, Brian. I just, if you have questions, if you can put them in the Q&A, and thanks for pointing that out. Gas locking. I'll just go back a slide, or actually, we picked that up in the pump section because I got a few pictures of a pump, and I can talk about gas locking. But here we're applying current, and this turns our motor, the shaft in our motor. And we also have a couple of bearings in here to keep from damaging the motor with the shaft. On the ESP cable, so we go from the motor to get electricity there. We have to have cable. There's a lots of, same as when you're wiring your house, you have different sizes and weights of cable. Basically, in electric submersible pump cable, there's basically two types. One is round, and the other is a flat pack, or flat. So you can see this is an example of a flat cable versus a round. If you have and again, this comes down to how much space you have between your tubing and your casing. If you got lots of space, then a round cable is probably more economical and probably doesn't heat up as much as a flat cable. A flat cable does allow you to get potentially bigger tubing in the same size casing. And then also sometimes you'll have, you can also run a hydraulic control line or a chemical injection line, some sort of where you can pump fluid down, as well as integral with the electric submersible pump cable. And this is strapped to the outside of the tubing string. So this is the connection to the motor, and then this is a reel of electric submersible cable. Lots of times at the drilling rig, you'll see it sort of in this position, maybe at the V door, and it'll be spooled up onto the rig floor. And as the pipe is being run, you'll strap this cable to the outside of the tubing. Here you can see the technician connecting the cable to the motor initially, and so this is connected back to that spool. And then as the tubing is being run in the hole, sometimes you'll have cross-coupling protectors to protect the cable when it goes across coupling, because the coupling is a little bit bigger diameter than the normal pipe, so you don't want that to rub against the casing. And there's banding or these connectors that hold the cable in place. Because again, if you're going, say, 2,000 meters deep, there's a lot of stretch on that cable. You want to keep it banded to the tubing. When we go from the motor to the seal assembly, and this is basically so the motor shaft, the motor's turning, has that shaft that turns, and then this is basically motor. They call it motor protectors, can be called seal assemblies. Sometimes they're bag type seals, which is just like a rubber element that keeps liquid out of the motor. Sometimes they might be coupled with a labyrinth seal, which is sort of like just a maze. So it's very tortuous path, so the liquid can't get to the motor. But basically, and you'll probably run at least 2 of these, maybe 3, just to make sure that none of the fluid from the well or that's going into the pump can make its way back down along the shaft back to the motor. Then we get to the pump intake. Again, this could be screened or just a bit of rough grading. Again, this is now, because up to this point, the reservoir fluid has been traveling in the annulus between the motor and the casing. Now we want that flow to go inside and go into the tubing. So we just have the pump intake. Again, this would be sort of a standard intake. If you're in a well that's making a lot of sand, then you can put a sand screen across there so that you don't get sand or fines going through your pump. Now we can talk a little bit about gas locking. So this is a gas separator. They used to be called gas busters, but I think maybe that might have been just a word that we called them. But so what happens here? You see, here's the intake, and again, this is another bit of an impeller. So it's on the shaft, and it's rotating. And again, so what it will do is it takes advantage of, if you're spinning liquid and gas, the liquid's heavier, it's going to go outside, and so it goes further out and then gets ported back up into the pump. The gas is lighter, so it doesn't get flung out as far in our merry-go-round, so it stays closer to the shaft, but then it's sent out into the annulus so that it stays out of the pump. So, and you can see that here with these red arrows and these bubbles. We get to keep that gas out of the pump, and gas is very light, so it's going to flow up the annulus and can be produced that way. Whereas the oil and water gets diverted back into the pump. And so in our pump stage, and this is a typical pump stage. So this would be the stator or the casing, and this would be the rotor. So that's on the shaft from the motor. And so as fluid is coming in here, it's coming into the rotor stage, the pump stage, and it's going around, it's spun around because the shaft is turning, and then gets thrown out to the stator wall. And so now it's got some energy. It's moving. And it's actually builds, it gives it a bit of pressure or head. When it contacts the stator, the casing, it is shaped so that the water, the liquid, gets moved up to the intake of the next pump stage. So it just moves it along. If we were to get a slug of gas come through the ESP, well, what happens is the gas comes in and gets spun around and gets pressure applied to it. And I said, comes in at 1 psi, out at 5 psi as an example. Well, where water is, you can't compress it. It gets that pressure applied to it. It's moving. It's going out, and then it's diverted up to the next stage. When you try and do the same thing with gas, when you give it that energy, the gas is compressible. So it is very much like trying to push on a balloon. When you push on that balloon, your hand will go into the balloon and the balloon will kind of go out this way. Well, that's because the balloon is compressible. You can't, it's not like I don't know, an ice block where you push it along. It actually has some give in it, that compressibility. And so when you give it that force, if there's way more gas than liquid, then it gets compressed, but it doesn't move forward, and so it just compresses, which is why we use pumps to pump liquids, and we use compressors to compress gas. So what you really need to do is when you want to move gas, you use a compressor, which will really increase the pressure in a compression stage so that it keeps that gas moving. A pump stage is not designed to have that much pressure differential across it. It's more because it's got to move, because what it's trying to do is move a lot of fluid through it, whereas gas is trying to get it as much pressure as possible. Question here: how powerful is the pump motor? We're going to come to we'll talk about that we'll do a few slides on pump design in a little bit, and what's really good about ESPs, which I've always liked about ESPs, is they're very easy to design, or I find them very easy. So, question: could this lead to cavitation? Yeah, absolutely, it could, and so that's a great question, Brian. So a lot of work's been done on cavitation, and what happens in cavitation is you'll have a gas, gas that's in a liquid, and then when it goes across a small orifice or small opening, a lot of times there'll be a pressure drop associated with going from, say, a small space to a big space. When you have that change in pressure, then the pressure of the liquid drops and gas can come out of solution. Very similar to when you open a Pepsi bottle, you relieve that pressure, the gas can come out of solution. So when that gas comes out of solution, now you don't have a smooth flow of fluid. Now you've got a bit of turbulent flow happening, and you can get in effect, well, depending on what it's going through, if it was going through a pump, then you can get pump cavitation. Then the pump starts having to try and process all this free gas that's just evolved because of some pressure drop. So so there are some guidelines for designing to stay out of cavitation. Again, it's to do with differential pressure, and I know that there's an API standard on it. I can I'll look that up this week, and I'll come back to it next week, because there is some fairly straightforward guidelines on how to avoid cavitation. But in general, we want to pump the fluid, and we got to get rid of the gas and not have gas in our pump. That helps with cavitation. And again, gas locking is the extreme example of that, where you've got so much gas in your pump. All it's doing is just compressing that gas, but not moving any fluid, or not moving the gas. So this is pump stages. So, and the type of pump stage actually goes to how many horsepower you need in your motor, or how powerful a pump motor you need. So that's the pump, and now we're pumping fluid up the tubing. But I just want to touch on this little yellow line here, which is the ESP cable. One of the things that we have to deal with, because we're putting all of the electric motor is great, because we're putting the energy into the fluid at the bottom of the well, and that's an efficient use of energy to get the fluid to surface. But we have to get the electricity to the bottom of the well. So we saw the electric cables, that's okay. But one of the things that's a little bit of a struggle is getting that electricity from the electric service provider, electric cable, to the wire, the power cable that's in the well. So in order to do that, we use the ESP cable feed through. And so this is a feed through here. It's basically at the top you have a plug in at the surface at the Christmas tree, and you have a plug in at the bottom of the Christmas tree, and you have a sort of a mandrel with a plug on this side and a plug on that side. And so this is the tubing hanger. So this is used for the tubing string to hang off of in the wellhead in the Christmas tree. And so this would be a normal tubing hanger. But this one has another hole drilled for the ESP cable feed through. So this part would go in this feed through hole, and this is called the feed through mandrel. And so then when you've run your tubing string and you're about to nipple up your Christmas tree, on the tubing hanger, this green part here, the technician will plug in the electric cable on the bottom and connect it on the top as well. So that is the ESP cable feed through. And sometimes in wells that need production packers to be installed, you can also run an ESP below a production packer, but you also need a ESP cable feed through. Here in this picture, this is a very low pressure well, and so you can see the ESP cable. So this is our coming from the tubing hanger here, flowing to production. Here, this ESP cable is lying on the ground, and then it's just fed through sort of a rubber gasket in the tubing hanger. So that's a bit of a low pressure solution. So, but if you're in sort of a standard sort of well, you would use a feed through mandrel. So those are the bits and pieces of the ESP pumping system. So now just some notes on design. And again, this is a neat little process for pump design. So this would be our condition where our inflow performance from the reservoir is no longer, the tubing size is no longer intersecting, is no longer lit, there's no natural flow going. So we have to say, okay, we think we can bring our reservoir pressure down to here. That would give us a flow rate of this as a target flow rate. This is what we want we would like our pump to pump, say, 10,000 barrels a day. That would be optimum from a bottom hole pressure and from a reservoir point of view. Hypothetically, it's a number. So then we say, okay, well, if I want, and so this pump curve, it looks complicated, but it's very simple, because all it's doing is it's taking these pump stages, this impeller and this stator geometry, and it is plotting it on a graph, which is super handy for us, because one of these, the first line we see here is this green line, and the green line is pump efficiency. So, and you see over here, 80% is sort of the max, and it goes down to 0. So, and then on the bottom is flow rate. This is metric meters cubed per day, and this is barrels per day. So if we look at 10,000 barrels per day, well, that's pretty well what this pump stage is designed for. Its operating range is, you can see, is about 65% efficiency. If you go lower than that rate, say 5,000 barrels a day, well, then this pump's a bit oversized. It'll still pump it, but it's not getting the amount of, it's not floating in neutral where it likes to be. It's a bit, the pump is too big for the flow rate. Same thing if you wanted to go to 12,000 barrels a day, this pump stage is a little bit small. So, but we used our IPR curve. We found out, okay, we want 10,000 barrels a day. Then basically we look for a pump stage that pretty well fits is in the operating range of where we want to be. So, and because the shape of this impeller and this stator, that determines how much liquid, how much fluid you can get through it per day. Now, if you've got bigger casing, you can put a bigger pump stage in there. You can probably get more rate through there. If you've got really skinny well with small casing, then sometimes you can't get larger rates. But one of the advantages of an electric submersible pump over something like a rod pump is, because I'm putting these small stages, the geometry, I can get a lot of fluid through them. I don't need to have a huge pump jack to get a lot of fluid volume. So they're really good for high volume. So in a geothermal application where you want to get a lot of water, a lot of heat to surface, electric submersible pumps are almost exclusively, I can't think of a geothermal well that doesn't use an ESP, because you can get a lot of fluid. And typically those casings are drilled as big as possible to get maximum fluid. Also good for oil wells if you've got a very productive reservoir. So we know what pump efficiency range we're in. So that's a good number for us. Now we need to know, okay, there's this blue line is head capacity. And head is a term for, if you turn on a pump, head is how many meters of height of fluid would you pump up in the air. So again, if you had a garden hose and you open the garden hose and you point it straight up in the air, it'll go up a certain height and then it'll start falling back down. That height is called the head of the pump. It's just the pressure that it puts out. So, and you can see from this blue curve, if you're not pumping a lot of fluid through the pump, you can pump it higher up. If you're pumping a lot of fluid through there, you can't pump it very high. So we look in our operating range and we say, okay, this is the height by head in meters. Well, yeah, in meters. Say it's about call it 7 meters, just over 20 feet. So what that means is one pump stage is going to pump 10,000 barrels a day, and it's going to raise it 7 meters. If I am, say, 2,100 meters deep, I know I have to pump, well, and one stage gives me 7 meters. I need to stack 300 pump stages to get enough pressure built up to get to surface. So, but that's okay. I got lots of room height-wise in my well. So I say, okay, I need 300 pump stages. Then looking at the same, now I get the last line on this graph, and this is horsepower. So, and, oh yeah, power's over here. So when I look at horsepower, at 10,000 barrels a day, I need about 2 kilowatts, or call it 2 horsepower. So, yeah, 2 kilowatts. I'll call it 2 horsepower. 2 horsepower. That's how much horsepower. That's how much energy I need for one pump stage to pump 10,000 barrels, 7 meters. So, but I know I'm going to need 300 pump stages. So I just multiply 2 horsepower by 300 stages. Now I know I need 600 horsepower. That way, now my design is done. I know what pump stage I need. I know what my pressure at surface is going to be because of my head curve and the number of pump stages I'm going to use. And I know how big my motor has to be because I know how much horsepower I have to need to put into the system to achieve that rate and that pressure. So, and so this is a typical chart for 100 stage. And so you can see, 10,000 barrels a day. I didn't check the math before I did this, so it's high risk here. So you can see the efficiency curve. We're in the operating range. And then on the pumping head is about 6,000 feet, which is, what's that, 2,000 meters? And the motor horsepower would be about 600. So for this is a different pump stage. So here, I had said 300 in the previous pump stage. This would be a bigger pump stage, so you only need 100. But the head and the horsepower is about the same. You have 100 stages here. It's probably a bigger casing, a bigger size pump. So that's one of my favorite things about electric submersible pumps is the design work is actually straightforward. It's one graph, it's 3 curves. Now, but again, like we reviewed before, when it comes to knowing our reservoir pressures, knowing our reservoir characteristics, knowing that productivity index, sometimes the numbers aren't exact, and sometimes they change over time. For example, you get a water cut increasing, or your gas oil ratio dropping, or your reservoir pressure dropping. Things can happen. So we have this great design system, but that was for last year. Now conditions have changed this year. So one of the things that the electric submersible pump users and providers came up with was a variable frequency drive. And so, and this is a picture of a VFD. This is a picture of a VFD. What it is it's an electrical modulator. It takes electricity from surface, and what it allows me to do, we've got our standard pump curve here that we just went through. This pump curve that will usually will have on it what frequency is the power at, is the electricity at. So, and I mean, normally North America's 60 hertz, Europe would be 50 hertz. So it'll normally say what is the frequency. And frequency, of course, is how frequent does the voltage change, or sorry, the current change in an alternating current system. So 60 hertz is 60 cycles per second, and 50 hertz is 50 times a second. Well, this electrical device allows me, or anyway, to speed up or slow down the frequency of the electricity that's being applied. And what it does is I take this chart, say at 60 hertz, and then I take another one at 50 hertz, which is a little bit slower. Okay, so that doesn't pump as hard. And I take another one, and where it's going faster. And so basically what I'm doing is I'm speeding up or slowing down how fast my pump is rotating. What this allows, see here's 60 hertz here, this pump curve. 50 hertz is slowing it down a bit. I can handle less fluid. So if my well conditions change, or if my design is off slightly, by adjusting the frequency of the electricity, I can cover a much wider range of pumping conditions and still be able to use my electric submersible pump, which again makes it a very versatile tool. And again, very high rate pump. So we put all that together, then we have a electric submersible pump system that is, oops, just let that video play. Gas, liquid coming in from the reservoir, and this just shows. And so here's goes past our motor with its copper windings in there. Again, cools that motor down. We have a shaft. Here's our ESP cable connected into our motor. That's driving that, and we can adjust the frequency on that. Then we're protecting our motor from our reservoir fluids. And you see that a lot of times there's not a lot of space between the tubing and the electric submersible pump and the casing. Then we'll come up to our seal assemblies. Again, this video has 3. Then we're coming into our pump intake. So now that reservoir fluid is going into our gas separation system, and you see we're shooting the gas out back into the annulus, keeping the liquid inside into our pump stages. And each pump stage is adding pressure so that we can get this fluid all the way back to surface. And then power cable back to surface as well. So that's electric submersible pumps. Like I said, they're a very useful tool, especially for high rate wells, and can be used onshore, offshore, packered, packerless, very versatile. However, they are an electrical motor downhole. There could be times when you have to actually do maintenance on them, pull them and replace them. A lot of that depends on how flexible the design is, how much room you have in your design, and what you're pumping through it. Pumping straight water is a lot easier than pumping gas and sand and solids. So they do wear out, but in general, a really good option for high rate production. And that's ESPs. I see Brian's got a question. Oh, well, second time attending. Thanks, Brian. Appreciate that. Yeah, these videos are on YouTube. So they're on our YouTube channel is Ballycatter TV. So it's BALLYCATTER. And yeah, all these videos are on there. And if you have any questions, please feel free to add them in. What is the life cycle of a pump? Well, a typical pump can last, I'm going to say, it varies by manufacturer, really varies by operating condition, but 7 years is a pretty good run life. There's been electric submersible pumps that have run more than 25 years, but they're in really nice conditions, and the sizing is really good. There's been other pumps that last a couple of months, but ones that go short runtime, most likely it's either sand. So the formation produces a lot of sand, especially when you put a new pump in there. You're going to draw down the pressure there. You might mobilize sand. You put sand through a pump, it's gonna wear, and it can wear out fast. Or scale. Sometimes when you have incompatible waters mixing, or Brian had mentioned about cavitation, pressure drops, you can get scale dropping out of solution then as well, and scaling up a pump. Those are kind of reasons for early failures, or an oversized pump. You go too big, and it pumps itself off, overheats, and can die that way. Really, I guess like everything, if you first, when you put it in, you need to monitor it and really pay attention. At surface, we saw a VFD chart. There's always usually a transformer on location, and it will draw an amp chart. So you're measuring the amps that's going to the pump. That can tell you a lot about the condition of the pump. If you're drawing high amps, then the pump might be sticking. If there's a bunch of chatter in there, you can really, there's a whole, probably another section that we can talk about at some point on interpretation of amp charts and trends in electrical supply to an ESP motor to diagnose issues. And I did have one where the ESP pump was working perfectly, but we weren't making any production, and it ended up being a pipeline leak. But we only figured out that we were having a release from the pipeline because the electric submersible pump was still working so good, but we weren't getting any fluid. So lots of good ways. So amp charts are a way to monitor your system. But I'll leave it at that, and hope to see you all next week. Again, if you want to see the videos on YouTube, just go to Ballycatter and check them out. And if there's anything you want covered, just shoot me a note. Also, you can send me an email at rod@ballycatter.com. Okay, thanks a lot. See you next time.